From the University of British Columbia, I'm Martin Ordonez, and this is Power Electronics.
Hi everyone, this is Sayed Abbas Arshadi, and today I'm going to talk about diode rectification circuits and their performance. A rectifier is an electric circuit which converts an alternating current or AC voltage at the input into a DC current or DC voltage at the output. This rectifier circuit typically utilizes an electrical component called a diode in order to convert the AC input into a DC output. A diode, which is usually indicated using the symbol seen here, is a passive semiconductor device. It has two terminals, the anode and the cathode. A diode acts as a one-way valve, allowing the current to flow in only one direction, from the anode to the cathode, and does not allow the current to flow in the opposite direction, from the cathode to the anode. To understand it better, let's take a look at it in a very simple circuit. In this circuit, a positive DC voltage source is connected to a resistor with a diode in this arrangement. Now, we want to see if the diode in this circuit conducts or not. First, let's assume that the diode will be on. When a diode is on, it will act as a wire or short circuit. So the circuit will look like this. And a current equal to Vn over R flows in the indicated direction. Now we want to check if it is the direction that the diode allows or not. So, will the diode conduct? The answer is yes. Accordingly, we can conclude that our assumption was correct. Now let's change the polarity of the input voltage source and make it a DC negative voltage instead of a positive voltage at the input of the circuit. Again, first let's assume that the diode is on in the circuit. So the diode will act as a wire and a current will flow in the indicated direction. But is it the direction that the diode allows it? The answer is no, which means our assumption was wrong. So the diode should be off or reverse biased. In this situation, the diode acts as an open circuit and the current is 0. Now let's apply an AC voltage to the circuit instead of a DC voltage source. In this situation, during the positive half cycle, the diode will be on and output voltage will be equal to the input voltage. However, during the negative half cycles, the diode will be off and the output voltage will be equal to 0. After a few cycles, the output voltage looks like this. This is the simplest kind of a rectifier, which is called half-wave rectifier. As can be seen, the output voltage ripple is huge. In order to make it smaller and make it a pure DC voltage, we can add a capacitor at the output. If we add a capacitor at the output of the circuit at the time of t0, the capacitor will be charged up to the peak of the input voltage during the next positive half cycle and tries to hold the voltage at its maximum value, which means the output voltage becomes higher than the input voltage and the diode will be reverse biased. This situation continues during the next negative half cycle and some parts of the next positive cycle, until the input voltage becomes higher than the output voltage. During this whole diode off time, the output capacitor and resistor form an RC circuit with a time constant of RC, which results in discharging the output voltage, causing a voltage ripple. When the input voltage becomes higher than the output voltage, the output capacitor is again charged up to the peak of the input voltage, and after a few cycles, the output voltage will look like this with a voltage ripple of delta VO. Now, in order to make this voltage ripple even smaller and make it more of a pure DC voltage, either we need to use a bigger capacitor to make the time constant larger or to make the diode off time smaller. How can we do that? By using a full wave rectifier. Basically, a full wave rectifier converts both positive and negative half cycles of the input into positive bumps at the output, despite a half-wave rectifier which only outputs the positive half cycles. The most popular full-wave rectifier is built with 4 diodes in this arrangement, which is also known as full-bridge rectifier. During the positive half cycles, a positive voltage is applied to the diode bridge, which results in turning 2 of the diodes on, while the other 2 diodes are reverse biased. In this situation, the output voltage is the same as the input voltage. During the negative half cycle, a negative voltage is applied to the diode bridge, which makes the other 2 diodes conducting while the other ones are reverse biased. In this situation, the output voltage is equal to the negative of the input voltage. As you see, with a full bridge rectifier, both positive and negative half cycles of the input are converted to positive voltages at the output. Now, if we add a capacitor at the output of the circuit, the output capacitor voltage is charged up to the peak value of the input voltage. When the input voltage passes the peak value, the output capacitor tries to hold the voltage at its maximum value. During this time, since the output voltage is higher than the input voltage absolute value, all the diodes are off. During the diodes off time, the output capacitor and output resistor form an RC circuit, which results in discharging the output voltage with a time constant of RC. When the input voltage absolute value reaches the output voltage value, the output capacitor is again charged up to the peak value of the input voltage. After a few cycles, the output voltage looks like the waveform shown here with a voltage ripple of delta VO. Now let's compare the output voltage waveforms of the full-wave rectifier with the waveforms of the half-wave rectifier. As clearly can be seen, the output voltage frequency of the full-wave rectifier is double the frequency of the half-wave rectifier. This results in a lower voltage ripple for the full-wave rectifier compared to the half-wave rectifier for the same size of capacitor and load. Generally, a half-wave rectifier is used for low-power rectification as well as reverse polarity protection. However, a full-wave rectifier is mostly used for high-power rectification. In this video, we took a simple look into half-wave and full-wave rectifiers. Stay tuned for deeper explanation of AC to DC diode rectifiers with non-ideal diodes, 3-phase rectifiers, and also power factor correction circuits.
Thank you, Abbas, for the introduction to rectifier circuits. If you have more interest in power electronics, please check our channel.